All right, let's look at the homework 18, problem number 7. All right, so we want to evaluate this double integral over the curved surface of the hemisphere. And so the v is equal to y comma xc comma 2z minus 1. All right, so let's draw a picture first. All right, so we have y-axis. And here's the x-axis. And here's the z-axis. All right, and so this is going to be the upper hemisphere. All right, so so you have a circle here. That's the bottom, and then it's going to look kind of like this. All right, so radius would be 3 here, so it's going to be 3 here, and 3 there, and negative 3 there, and negative 3 there. All right, then v is equal to y comma xc comma 2z minus 1. All right, so we're talking about just the curved surface, so we're only talking about just this. So here, right? So this is we're talking about, but in order to use the divergence theorem, we have to actually include the bottom side, bottom side here, right? All right, so I'm going to call this hemisphere, so I'm going to call it H, right? That's a hemisphere. And the bottom side, I'm going to call it B, right? So if you have a double integral here over the hemisphere of V dot N d sigma, if you add on the bottom side over the B, right? The same thing, V dot N d sigma, then we can use the divergence theorem, right? So this is going to be triple integral over the solid. So I guess I'm going to call it the solid S. So that's the solid S, and call it S. Then you can do a divergence of V d tau. All right, so this is the guy we're interested in. So this is the guy we're interested in. So instead, so we want to find these two guys, right? So we can write it as, right, integral over this hemisphere, and V dot N d sigma is equal to, right? So you have a triple integral over the solid, and divergence of V d tau minus, and you have a double integral over B, the base, V dot N d sigma. All right, so let's do that. All right, so we need to compute this guy, so let's try to find that. So we have to take the divergence of V. So we have that. So let's see, there's a room here. I'm going to just compute the divergence of V. Right, partial y with respect to x is 0, plus partial of xz with respect to y would be 0, right, plus partial of 2z minus 1 with respect to z would be 2. Right, so that will be 2. All right, so we just have, so this is going to be a triple integral over the solid S, and of 2 d tau, right? So it's a 2 times the volume of this solid, so you can find that, minus, right? This is an interesting one. Right, we have to take the dot product with the outer normal vector on the base, but here outer normal vector is negative k, right? And at the same time, on the entire base B, z is 0, right? So z is 0, so v, so this v right here, oops, right? So this v on this base B is going to be y comma, and a z is 0, so it's a 0 comma negative 1, right? And n is negative k, so if you take the dot product with the negative k, would be negative k is 0 comma 0 comma negative 1, so 0 times 0 plus 0 plus negative 1 times negative 1, which is positive 1. So this is just going to be a double integral over the base B of 1 d sigma, right? Then this is going to be simply 2 times the volume of this solid whole hemisphere S plus minus the area of the base B, right? And this is just a circular base. We know how to find area, and the volume of the hemisphere is just a half of the sphere. So I'll let you finish that. All right, that's it. I hope that this was clear.